technology has created hundreds of thousands of jobs, but things are just getting started. To support a new generation of American solar innovators and entrepreneurs, the Department of Energy created a $3 million prize competition. The American-made Solar Prize is helping transform great ideas into technology solutions that are ready for market.
The Solar Prize is wide open as far as opportunity to propose your best and brightest idea.
It's ideal for an innovator who wants to have the runway, the financial runway to develop the technology and actually get over that valley of death, actually having a producible product.
Through a series of contests, competitors win progressively larger and larger cash prizes to advance their ideas.
One of the really fantastic parts about the Solar Prize competition is it's a prize, and the ability to get the money without all the complicated overhead and administration means that we were able to put it to use immediately.
Each step of the way, competitors will also receive expertise, technical support, and guidance from national laboratories, energy incubators, and industry partners.
The network is there to help teams fill in gaps. So if a team doesn't necessarily have access to a prototyping facility, we are there for them. And if they don't have access to maybe find the right connections that they need for testing or business plan development, we have people that will help them with that as well.
The partnerships we've developed as a result of the American-made Solar Challenge have been tremendous. They have helped us write and rewrite our business plan, our patents filings, our CAD specifications. The partnership in this community has really been tremendous, and our partners have dramatically accelerated and de-risked our business plan.
By supporting these entrepreneurs, the American-made Solar Prize advances solar innovation and empowers the leaders shaping our energy future.
Yeah, we're all trying to work for the same future, right?
We are, and it's inspiring to be around like a lot of completely different areas with all the unifying aspect of clean energy, renewable energy, but completely different approaches at different aspects of the problem, and that gives us energy.
Visit AmericanMadeChallenges.org to learn more.
A year ago, innovators across the United States were invited to submit ideas that could change the American solar industry. This call to revolutionize solar as we know it was the first step in a national competition, the American-made Solar Prize.
The Solar Prize is an innovative prize competition that really helps accelerate solar manufacturing and really bring new ideas in solar to the marketplace.
Out of over 150 submissions, 20 ideas were selected to win $50,000 each and continue to the next phase of the competition. These teams worked tirelessly, developing prototypes, running tests, and refining business models. In Boston, the teams pitched their products and ideas to industry experts at the SET Demo Day. 10 teams were selected as finalists, each winning $100,000 in cash prizes and $75,000 in technical support from world-class laboratories. In the third phase of the competition, 13 teams traveled to Salt Lake City to compete in Go Demo Day at Solar Power International. These teams took the stage one last time to pitch a panel of expert reviewers in the hopes of taking home $500,000. At the end of the day, the final two winners of the American-made Solar Prize Round 1 were chosen: Solar Inventions and Phase 3 Photovoltaics.
After 1 year of incredible work and insane amounts of research and partnering, we are unbelievably excited to be one of the two final winners in the American-made Solar Prize Round 1.
I was so excited when we heard our name called up there. I was nervous because the first pick was a technology pick, and I was really excited to hear when he said this is something I could understand. I knew it was us immediately.
These two teams were chosen for their game-changing technologies. Both teams received a final $500,000 in cash prizes and $75,000 in support vouchers. They plan to use this money to continue testing and driving their innovations to market.
So the first thing we're going to do is fund even more field tests than we had originally anticipated, so we can get as much data from a wide variety of situations and customer types.
Now we're engaged in some pilot builds with some of our home builder partners, and this prize money will enable us to start hiring more trainers, more field service engineers, and start putting together more kits so that we can deliver them more quickly to our customers.
With the help of the Solar Prize, these innovators have quickly accelerated their technology to get it market ready.
The prize was an excellent format for us to kind of codify our ideas and kind of shape it and start forming it into a startup business. We all came out of the solar industry on the manufacturing side, and so we're pretty familiar with how a module is made and how modules are installed, but we weren't the best at being able to bring that into a pitch and bring it into something that's easily communicated to people that aren't in that space. And so this prize, through all of its different checkpoints and requirements, really enabled us to be able to sell this business to others. And it's been an effective tool with our customers and clients. So we appreciate that opportunity.
And we never would have pushed this hard and made the decisions that we made and accelerated our work with our partners and gotten into the type of national labs that we're now involved with in this time period without the type of outside influence that this contest provided for us.
Congratulations to the Solar Prize Round 1 winners, Solar Inventions and Phase 3 Photovoltaics. You are transforming the future of American solar.
AC/DC microgrids for residential applications. And we have as our guest today, Doug Hamborski, an architect from Hamborski Solutions Group. And also, yeah, you want to start over?
All right, can you start over 1 second?
Sure, I jumped the gun, didn't I?
Yeah, it's okay. All right.
Okay, I'll wait for to see the little live sign go up.
Okay, ready?
Good afternoon, ladies and gentlemen, and welcome to this afternoon session on hybrid AC/DC microgrids for residential applications. In today's program, we're going to be taking a look at the Purdue DC Microgrid House Pilot Program and a little bit about the eMERGE Alliance Residential Nanogrid Technical Standards Committee. Our presenters today, primarily, I'll have a few words to say, but our real stars are Doug Hamborski, an architect from Hamborski Solutions Group, and Jonathan Orr, a PhD candidate who's leading a lot of the research for the DC Nanogrid House up at Purdue University. And of course, myself, Brian Patterson, I'm the chair of eMERGE Alliance, which is an open industry association with members that represent industry and academia and government agencies and other associations. We sort of collaborate with a lot of folks across the industry. And next slide, if you would. What we do at eMERGE is really we're developing Vanguard standards systems for hybrid AC/DC microgrids and DC microgrids. We started out with DC, but as most people know, pretty much all microgrids are actually hybrids between AC and DC. And we try to do leading edge kind of standardization in advance of the market developing. Most traditional groups wait until the market develops a little bit more. We're trying to get in front of it. We also do a lot of market development, mostly through education and technology demonstrations. And of course, one of the reasons we're here at North American Smart Energy Week is because we partnered with SEIA and SEPA, the two organizations that sponsor this event, in providing some of this education and demonstration work. The end game for us at eMERGE really is to see if we can move the ball forward on providing a new digital-based energy network. We like to think of it as an energy network, an internet, or a grid of grids. And we think we're at the crossroads for whether we stay with the traditional sort of unidirectional grid that currently exists, or whether we move to a more mesh network topology where we have distributed intelligence and distributed resources combining to provide a more resilient and reliable power network as the market expands in electricity. So without further ado, I'm going to turn the presentation over to Jonathan Orr from Purdue. Jonathan?
Thanks, Brian. Really appreciate that introduction. So, hi everybody. Thanks again for coming to our session here on microgrids. And again, my name is Jonathan Orr. I'm a PhD candidate here at Purdue University, and we are working on a project here that we call the Purdue DC House Nanogrid project. And a nanogrid in this case is a specific application of the microgrid, wherein which we are actually trying to implement kind of hybrid DC AC network inside of a residential home. So as you can see here, the Nanogrid House project is a culmination of a multitude of different aspects. We are working with the power grid and utility companies to make sure that from a technical side and a utility side that we're aligned. We're looking at the home as a whole, not just from electricity aspects, but also from energy improvements. We're looking at trying to retrofit existing equipment to make it work with DC to better align with the nanogrid itself. Coming up with a novel nanogrid design that could be replicated in other homes. And also, in addition to the energy, building a smart grid network and trying to understand how the house reacts to different circumstances, conditions, environmental settings, and the residents' usage characteristics inside the house. Next. Next slide. Yep, perfect. So this is the DC house in all its glory. It's a 2-story residential home based in West Lafayette, Indiana. It was built in the 1920s, so it has a lot of history and a lot of character and a lot of improvements that needed made. And there's actually 3 graduate students that live and work inside the house full time. So it's a real environment. It's not artificial. There's real people living there using real utilities and appliances. So this is a perfect environment and almost playground for us to test out a nanogrid setting like this. Next slide. So inside the house, we have instrumented all of the existing AC circuits through the help of Eaton with their EMCB circuit Wi-Fi circuit breaker modules, and another system called the TED Pro Home modules, which allow us to collect electrical and energy data from all the different devices and circuits in the house on a minutely basis. So we can get real-time feedback of what's going on from the AC side and subsequently with the DC side once we finish implementing the nanogrid. Next slide. So this is our goal here. We're here on the left right now with our with the existing structure. We're bringing in solar. We have a battery. We've got the typical utility coming in through a normal AC load panel. The problem is that anytime we want to use DC-based loads, we have to go through all these conversion steps. And there's a double penalty involved when you add solar or wind into the mix. You throw solar up on your roof, then you've got to convert the solar from DC to AC to be used within your home. But then at the point of use in many different loads like LED lights, computers, TVs, and all kinds of different things, then you got to convert back again from AC to DC. So our goal is over here on the right. We want to have one central inverter at the front of the home and have a universal DC bus running through the house, which allows us to minimize those AC to DC conversion losses and have much higher efficiency DC to DC conversions, which we know we can get to a much higher level. And of course, we know that some loads will need to continue using AC, so we have support for that as well. And this slide shows you the actual implementation of what that looks like. So our nanogrid is composed of several pieces of equipment. We have a bidirectional inverter at the front with isolation transformers and input and output from that inverter. We have a DC-DC converter module, which connects up to our solar panels. We have a 14.3 kilowatt installation on the house's roof. The DC-DC converter also has multi-power point tracking built in, and it helps regulate our 380 volt DC bus, which constitutes the backbone of our nanogrid. Then we also have a 21 kilowatt hour battery system connected on the DC side to help us store some energy for later use and even function in an island mode independently from the grid. And in addition to all of that, we have a low voltage, what we call the LVDC side of the grid, which runs about 48 volts DC for use with smaller applications, smaller devices, and is also touch safe for the residents to be around. Yep, next slide, please. This is our electrical schematics of what you just saw there from that top level diagram built in. So our goal with this was to make it very flexible. Again, this nanogrid that we've constructed inside the home, it has the flexibility to support not just DC loads, but also AC loads, which is the perfect environment for us to run comparisons between AC and DC retrofitted devices and evaluate and compare their performance and see what kind of efficiency savings we can actually gain from doing that retrofit operation. Next slide. This is a top view level of our home. You can see our solar guys there working on the roof. This was back earlier in February of this year that we finished the solar installation up there. So, and these guys have some outstanding software that called Helios, which actually lets us estimate throughout the year based on the environmental conditions and the physical location of the panels and the angle and all of that, exactly how much energy we can expect to produce each month. So unfortunately, we do live in West Lafayette, Indiana. It does get pretty cold, and some of you guys may remember last year we had a particularly cold winter, the polar vortex of 2019. We actually expended over 2 megawatt hours of energy from the heat pump system alone, just trying to heat the house. So we know that the solar will not be able to completely make the house energy independent, but especially during some of the summer months when the energy loads are lower, we definitely think we can get maybe a week or even more of the house running in a standalone mode. So that is definitely one of our big goals. Next slide. So we also have a bunch of dashboards and visualizations that are hooked up to our energy monitoring circuits so that we can watch these things in real time and also go back and do a thorough analysis and look at the typical usage conditions of various appliances and equipment that we have in the house. We can see the times of day when there's peak load. We can check out maximum power use and instantaneous power use at different times of the day. So all different things like that are critical and essential to helping us design the nanogrid. So with that in mind, in particular for the, next slide, for looking at types of equipment that we can retrofit in order to see a real benefit from running a DC grid. The first thing, of course, we looked at is a heat pump. So we know that in the US, heat pumps, they can use up to, heating and cooling alone can run you about 50% of your energy costs throughout the year. And on this left side of this slide, you show like a typical conversion from an AC input to a controlled AC output that would run a motor in a heat pump type of device. What we want to do is bypass the AC input and the rectification, power factor correction, all of those input stages, and just directly feed DC into the heat pump directly into its control circuits. So in doing so, we believe that we can save a non-trivial amount of energy in the long run, especially when you consider that 50% of those energy costs come from this thing alone. So if you can save a few percent from avoiding conversion losses, that can add up in a big way over the course of the year. So on the next slide, here I've shown you a picture of our psychrometric chambers here at Purdue University. We have a 500 volt DC 15 kilowatt power supply and a Train heat pump unit, which they have very graciously retrofitted with us to consume direct DC power, which is awesome. So we have this thing set up in our psychrometric chambers. We can test it with all kinds of different environmental conditions, both indoor and outdoor. One of our techs down there in the bottom left, you can see is showing you that our chambers go down from -4 degrees Celsius all the way up to 130 degrees Fahrenheit. So we can test a huge variety of different conditions. But again, this is a great opportunity to compare the DC performance on the 380 volts compared to the typical AC performance at the house, which is using split phase 240 volts AC. And then on the next slide, this is a inside look inside the psychrometric chambers of the indoor and the outdoor unit comprising the heat pump, showing you all of the different sensors that we have hooked up to this and things that we can monitor and collect. And on the following slide, we summarize the AC testing that we've done with an unmodified heat pump unit and the DC testing that we've done with that heat pump that we showed you previously that's been retrofitted for DC. So far, what we have seen between data collected from the house compared to the DC experiments that we've run at the psychrometric chambers is about a 3 to 7% improvement in terms of energy efficiency. So again, not too bad when you compare that to your 50% of your energy costs for the whole year. 3 to 7% can make up quite a bit. So definitely more to come on that. Following the heat pump studies, we've also been doing a lot of work surrounding energy improvements with the house itself, because ultimately all of these different things, the nanogrid even, although it's electrical focused, I mean, our ultimate goal here is to achieve improved energy efficiency. That's our goal. So throughout the lifetime of the house, we've made a number of different improvements, ranging from installing a variable speed heat pump, installing insulation, replacing windows with high efficiency, insulated windows, different things like that. And what we've done is we've measured the energy consumption, particularly from the heat pump for heating and cooling of that space, compared to the weather conditions outside. And what that allows us to do is determine like a system effectiveness. So if it's 20 degrees Fahrenheit outside, and we'd like the house to be at this like 65-degree Fahrenheit balance point, how effectively is the heat pump heating in that specific circumstance? And that's what you see on this graph is a plot of the cooling shown in the blue and the heating, the hourly heating cost shown in the orange yellow color there. And obviously, again, we're in Indiana, so there's a lot more in the orange than there is in the blue. On the next slide, what we do is we take that environmental amount of heating and cooling required compared to the actual energy that was expended by the heat pump for heating and cooling, and overlay them on each other. And it follows pretty well. You can see that the temperature compared to the energy consumption is pretty well in line. But again, what we're really interested in is these big spikes, like how well the heat pump performs there. And again, you can see in January 2019, there's the January, February, there's some big spikes, and that was during the polar vortex. But on the last slide of that testing here, you can see our overall heating and cooling system effectiveness. And again, this is pre-DC. This is just energy improvements that we've made in the house itself. You can see that we've achieved pretty substantial improvements over the course of the different renovations that we've applied to the house. Again, all seeking the goal of energy independence and energy efficiency. On the next slide, here I show you the smart network aspect of the house. So you can't have DC without lots of different sensors, and that's exactly what we're after here. We have implemented a whole home smart network in which we monitor virtually every parameter we can get our hands on, not just energy, but also room by room environmental conditions, like the temperature, like the humidity, like the airflow, how much light there is in the room, the air quality, anything that we can. And we're trying to then take that and use it for feedback to control different devices. So if we know a room's not occupied, then stop heating it. If there's too much light in the room, then dim the lights, things like that we can use directly to help save additional energy. But the great thing about these devices is they can run on this fantastic technology called Power over Ethernet. Power over Ethernet runs at 48 volts DC, which is on our low voltage DC bus. And that PoE line, which is just simply an Ethernet, like a Cat5 Ethernet cable you probably have plugged into your computer right now, that can serve up to almost 100 watts of power. It's pretty incredible. So that is running around the entire house, and it's powering all of our sensors, which is collecting all this great data and letting us control our appliances and devices. And on the next slide, here you can see this is a simple implementation here that we have in our dining room. We're using Raspberry Pis, ESPs, Arduinos, all kinds of very low-cost microcontrollers and sensor arrays to gather all of this data. And then, like the energy dashboards, we also have dashboards and visualizations to help display this data and show us what's going on. So that's what we're doing here at the DC house. I will now hand it over to my co-presenter, Doug, and let him talk a little bit about some other items. Thank you.
Thanks, Jonathan. It's exciting as an architect and someone who's been involved with eMERGE for probably around 10 years now to see your team developing the sandbox, finding real-world applications for all these great emerging technologies. With that as an umbrella, the eMERGE Alliance has put together a variety of committees to define and create standards for these emerging technologies that utilize direct current DC power. One of them, Jonathan and I co-chair, it's called the eMERGE Alliance Residential Nanogrid Technical Standards Committee. And in essence, the mission of this committee is to develop standards for DC and hybrid, that's very important, hybrid AC-DC power utilization within a nanogrid configuration for residential use buildings and loads. Also to promote the development of DC-powered products to be used in residential applications. Provide technical resources to the design community for the DC-based technology for residential applications. In essence, eMERGE and we see a future where the house is really going to become a DC powered house, and we're going to try our best to facilitate developing standards to make that a reality. So the outline of what the committee is going to be doing is we're going to have a hybrid use of AC and DC power, sort of look at that, define it, define the different interfaces between AC and DC. There's a variety of power sources for both AC and DC. How all these things will connect together, power distribution, both AC and DC, whole house subsystem topologies, sort of a vague term, but there's all these little subsystems within the overall network of power, as Jonathan went over, from communications to power to control. There's all sorts of smaller systems within the overall system. Operational criteria for appliance and device loads for manufacturers to develop their products around. Control options, there's lots of control needed and utilized in these newer smart homes. And a transformative path to implementation. We're not just going to flip a switch and one day, oh, there's the DC house. It's going to evolve over time, and this committee is hoping to help to assist with the transformation. On the power side of what the committee will be looking at is a wide variety of DC sources, from AC to DC rectifiers. Of course, PV solar is one of the dominant DC sources in the industry or in the market today. Fuel cells, wind, ISP, microgrid, the list as shown. The AC sources, of course, the dominant source is the good old-fashioned utility grid. Been with us for many decades, been over a century now. And DC to AC inverters. You know, we're coming to a time where maybe your community power isn't going to come from an AC grid. Maybe it's going to come from a community DC source, like a solar farm or something of that nature. But you still need to run an AC device in your house for some period of time. So you'll have DC to AC inverters the way you have AC to DC rectifiers or power supplies. And then, of course, the missing link is energy storage. And there's a variety of chemistries and technologies evolving to support the storage industry. As far as the loads, there's a list of loads in your house as we speak. The issue is that as we evolve in our technology, the goal is that more and more of these loads will be powered by direct current power as opposed to AC power. And in fact, most of these loads are already internally DC, and they have, as Jonathan pointed out, these power converters or power supplies within them. We hope to eliminate that, go direct to the DC portion of the load and eliminate that. This committee is sort of, I call it 2.0, but eMERGE launched the residential committee many years ago. I was involved with it at that time. And so this is really the Resi Nanogrid 2.0. And so we have a framework of data and information that we have from previous efforts that will help us move this committee along a bit faster. One of the things, since Nanogrid wound up in the committee's name, we kind of said, well, what is a nanogrid? And it has many different definitions. We're not going to present it in this presentation because it's going to be part of the work of this committee. But it's an important word, and it's going to become more and more relevant as we head into power networking between microgrids, nanogrids. And so this slide is representing that it's not a one-size-fits-all, and we're going to help define that in our committee for the purpose of our committee. The other big issue is hybrid house. It's in this presentation's name. The Purdue house is a hybrid house, and we acknowledge in this transformative period of time that we're in, we're going to have AC/DC houses, and so it's going to be important for these houses to accommodate either or both AC and DC, from power sources, from grid power, the different sources and the different loads. What's going to define the need is the load. Is it a hair dryer? Is it an appliance? Is it a TV? Is it electronics? And then the house will be designed and distribution established to support those loads. And over time, the loads will become more and more key to DC. So here's just sort of a quick graphic of how a hybrid house would have a variety of sources coming in, and then within the house, of course, it'll be subdivided into those smaller networks of AC and DC power. So I'm going to hand this now back to Brian to just close out with some more eMERGE news. And in the absence of Brian, let me point out that in addition to the residential committee that Jonathan and I are involved with, the eMERGE Alliance is really at the forefront of developing technologies and information and standards for supporting the entire evolution of really the use of direct current power and hybrid power, essentially all tying to the highest efficiency available in the marketplace. So if you
Doug, I made the classic mistake of going on mute while you were talking before. But in any case,
Doug go ahead.
Doug is pointing out that the various committees at the nanogrid level really consummate or connect together in what we call the grid of grids or community microgrid work that we are starting to do at this point. Again, the end game is to have a mesh network connectivity between all these resources, distributed energy and distributed intelligence, working on a holonic platform. In other words, that individual nanogrids can operate either independently by themselves or collectively in a system that becomes collaborative, if you will, or supportive of each other in a community, and then rolling up to the national grid or regional grids. So we're working at all those levels. And there are pilots now underway. Probably one of the more notable ones that are using this 3 or 4 tier grid of grids approach is at the Kirkland Air Force Base in Albuquerque, New Mexico. We'll be talking about that in one of the other presentations. But suffice it to say that we're not just looking at one application. If you've seen one nanogrid or one microgrid, you've just seen one microgrid. We're looking at all the different applications for microgrids and how they come together in a self-aware neural network topology that is capable of being highly resilient and self-healing and collaborative to reduce cost and to provide the highest levels of reliability and resiliency in the system. The next slide, if you will. So that does conclude our presentation, but if you want to contact any of us, we are using eMERGE organization addresses. So Doug, Jonathan, myself, all available through one of these addresses. So thank you very much, and thank you to our two speakers today, Doug Hamborski and Jonathan Orr. And hopefully you'll get an opportunity to see more about the Purdue House as it progresses. Thank you and have a great day.
Good afternoon, everyone. I'm Brian Patterson, Chairman and co-founder of the eMERGE Alliance. My presentation this afternoon is about mesh network microgrids. Due to the virtual format of my talk, no refreshments will be served, although I will endeavor to satisfy your thirst for knowledge and information. So let's get going. Now, we've been blessed with the largest machine man has ever made, the electric grid, which has, for the most part, met customers' demands in real time, every second of every day for the better part of a century. But that's just it. Customer demands, which hadn't changed much in 100 years, are rapidly changing now. Much of that change is resulting from two major contributing factors: the way we are choosing to generate electricity and the way we use it. So keeping that big old machine going for another 100 years is going to take a little more than a fresh can of oil and a few spare parts. And yes, we can't do without it. Simply put, electricity underwrites the economy of the 21st century. Without a stable electricity supply, health and welfare are threatened, and the U.S. economy cannot function. But when a power system fails to deliver, clean energy or not, the consequences can be catastrophic. This is truer today than ever before, given our increasing dependence for almost all that we do on the supply of energy, and particularly in its most useful form, electricity. So today's subject is not worth talking about until we understand the problem we are trying to solve with mesh network microgrids. The increasing vulnerability of our electric power system, with its disabling faults and interruptions in service, are just not acceptable anymore. Summarizing what's described in detail in the Smart Electric Power Alliance's Microgrid Playbook would simply be to say, things aren't getting any easier or smoother on the road to safe, clean, high quality, uninterrupted, and abundant electricity. You may even be able to add a few of your own events to this growing list. Some of them short duration, like downed utility lines from a traffic accident, or the failure of a piece of equipment in the transmission or distribution infrastructure. All of these can cause local blackouts that can be disruptive and very costly. So let's face the reality. Electricity is critical to the sustainability of our civilization in its current form. Suffice it to say, a few days without electricity can be very disconcerting and even threatening. But a week, a month, or a year without electricity, I think we all shudder to think. But let's take a broader view and explore some of the more positive and obvious inevitabilities in our situation here. Both the building and power industries are kind of long overdue for some changes. We are starting to see our buildings becoming electroactive and becoming more and more a part of the solution and not the problem. Our built environments are getting more resourceful and efficient with electricity. Our information and energy systems are going from being someone else's problem to being an integrated part of our life, leaning in the direction of personal energy independence. And we're starting to make better use of fuel supplies by moving our transportation propulsion means to electric, even though that will mean we need to produce as much as 30 or 40% more electricity to replace our use of gasoline and diesel fuel in those same vehicles. But while we may be just in the middle of the information age, we're surely at the beginning of a new energy age, maybe even what we might call a new electricity age, based on the electrification of just about everything. And while good information is always a guide, without energy, it's nearly worthless. It's electricity that gives us the ability to do work, or to act, or to create new value. Given all this, what should our goal set look like when it comes to resiliency? Reduce vulnerability, maintain service to critical infrastructure, prepare for large-scale disruptive events, and share the responsibility for resiliency. It's a tough and demanding list. When I think about tough problem solving, I first like to see if the problem has been addressed or solved in a similar but different situation. In thinking about system resiliency, there are lots of success stories and some failures. But in the case of the power system, the nearest candidate is something most of us know a fair amount about: the internet. This is despite the fact that, ironically, one of its biggest vulnerabilities is the potential loss of power to it. The evolution of distributed information systems has greatly outpaced the evolution of distributed electric power systems. On the left, we've gone from the invention of the transistor to the wide use of personal information devices in about 30 years. Yet, even though the invention of the solar cell lagged the transistor by less than 10 years, a similar and even strikingly similar evolution in distributed power has taken over 70 years. Well, if nothing else, we can learn from this history and project it forward. As we've seen distributed information devices evolve to a global network, creating enormous new value in society, so too can we comfortably predict an almost identical future for distributed electricity systems, with a commensurate enormous increase in new value creation potential. When it came to the transformation of the information industry, the tremendous convergence of influencing technologies provided the catalyst for faster adoption, especially when multiplied by the network effect. Look at the list of technologies that are all converging now in the power industry. And why shouldn't we be considering networking to accelerate their progression, lower the cost of systems, and multiply their ability to create value? Well, let's quickly jump through what else we can learn from our 40-year internet experience. First, we see the internet largely depends on a massively distributed capability. Today, nearly 70% of all information, a lot of it video, is created and used locally at the fringe. And whether you're a third grader who sheltered in place at home while attending a virtual math class run by a teacher on the other side of town, or the president of the third largest country on earth who is tweeting 280-character messages to an anxious citizenry, you both have essentially equal access 24/7 from any place in the world. The internet has a hybrid mesh network topology where all nodes cooperate to distribute data to, from, and between each other. The internet can automatically manage flow, self-organize, and avoid faulted or offline routes. The internet has a rigid set of rules for transferring data and a simple standardization of data form. And finally, the internet's operation is based on the premise of holonic transactive cooperation, what I'd like to call the enlightened self-interest of all of the agents, nodes, users, devices, or whatever else you want to call them. And let me see if I can break this down in a simpler way. Holonic, self-reliant units that can act as the whole or as a part of a system. Transactive, capable of acting by trading or exchanging, and in this case, electricity. And finally, cooperation, helpful by doing what is wanted or asked for when possible or necessary. So here's what it might look like, moving from the centrally fed serially connectivity of our 100-year-old power grid to the mesh network connectivity of a grid of grids in layers. To summarize, this grid of grids will first recognize and promote adding new power capacity at its edge. It'll better accommodate natively electronic loads, storage, and generation. And it will enable non-synchronous operation. It will employ the benefits of a mesh topology. It will rely on holonic control architecture and ultimately enable energy as a service for value creation. Well, so far I've tried to make our case for a transformation of the traditional electrical system to move away from a central station configuration to a distributed generation one. The question is, are we right? Look over the diagram on the left there and find where we are right now and ask yourself, which future is most likely? Centralized, distributed, or hybrid? And as a second thought, based on your view, will the system stay AC? Will it move to DC? Or will it become a hybrid? And think in the 20 to 30 year kind of time frame. Most of us at eMerge have great confidence in our predictions, even though we come at our predictions from quite different directions. That's because in trying to predict the future, we simply focus our attention and give a keen eye on the inevitable. But as a futurist, I still like to keep at least a few toes squarely placed in the present. So let's explore what's going on in the market and see if all of what I have said is and what I've been talking about makes any sense. Probably the best embodiment of what we are predicting is being demonstrated in a relatively new platform offering from a company called Amera Technologies. Amera is a subsidiary of Amera Inc., a utility with $34 billion in assets and operations in Canada, the US, and the Caribbean. Because of time limits here, I won't be able to describe all of the details of their platform, but let me hit its major attributes, and if you want, you can contact them for the rest of the details. The platform is comprised of at least 4 tiers of grid connectivity. Starting at a premise, the first tier is a self-contained box that houses the core of a nanogrid. It connects to whatever power sources are available on site, as well as makes a redundant loop connection to the next tier and the local neighborhood on a peer-to-peer basis. The second tier is comprised of a completely peer-to-peer connected group of similar nanogrids. That is again connected to a redundant loop to a common resource community microgrid. This third tier is typically comprised of locally shared resources and also maintains the connection with the local utility grid. Note that the connectivity between all tiers is direct current, eliminating the complexity of synchronization, frequency, and phase control, and the connectivity of natively DC elements like PV and batteries, is simplified. And while the bidirectional inverters are used at the connection points to the utility grid and a traditional AC wired premise, both ends have the option of being DC connected, in essence, giving them an advanced level of future proofing should either of these move in whole or in part to DC in the future. There's a lot more detail to it, but there you have it, an early implementation of a grid of grids, perhaps the beginning of an internet. Neighborhood and communities can be further connected into area grids with both AC and DC interconnection. And utilizing higher voltage DC, they need not be contiguous. This allows for a progression of the new technology to be easily evolved over time. The utility can maintain its traditional operations and controls of the existing grid, while the distributed grids manage their transformed portion almost on their own. But these are just diagrams. Let's look at the installed system in Albuquerque, New Mexico. Home to the Kirtland Air Force Base and the U.S. Department of Energy's Sandia Labs, what better proving grounds for this latest of microgrid networking technologies? From this drone's eye view, you can see the basic elements of the Emera grid of grids. You see the residential and local commercial building neighborhood cluster of self-reliant DC connected nanogrids. And I believe they're numbered here N1 through N10. The community microgrid, labeled here as C1, is a large PV, contains a large PV array, which, by the way, is part of the Sandia Labs testing field there, a natural gas generator, and a community level battery stack. And of course, it has the connection to the utility grid, which you see to the far right there. And there is a special lab. If you go all the way to the left, there's a special lab connection that allows variable load testing under varying conditions of the grid itself, courtesy of, again, the Sandia National Labs on that site. Here's one of the nanogrid supported commercial buildings with both AC and DC charging. The building was purposely wired with AC, but will gradually move its loads to DC over time, just to model out the transformation process. Here's the core of the community microgrid housed in this nice, small, compact outdoor housing. Here's one of the 7 residential buildings. Note the solar panels on the roof, and you see a traditional AC air conditioner, AC air conditioner hanging out of the window there. Here's a shot of the community PV that's tied in at that 3rd level tier. Again, this is part of the Sandia testing lab here. So you see a lot more apparatus than you would normally see in a PV array like this, but it's also doubling as a test bed. Here's one of the myriad of dashboards for the system. This one is a relatively simple one of the whole system. But let me point out a few of its features. The graphic user interface, or GUI, is internet accessible, but can be isolated for security reasons when necessary. And it shows subpanels for the nanogrids, and you see them again labeled 1 through 10. You see solar, community solar, and that's right in this area here, where it's you see just to the bottom right. The community battery, so a little bit further up next to the Emera logo there. You see community generator, and I see the dials at 0, which means it's on standby, as it probably should be. And by the way, this is an active recording of an active period of the actual display. So you're looking at real information as it's depicted in the dashboard. Then you see over again on the right, below the logos there, you see the grid connected inverter. And ultimately, you see a representation of the utility grid. Now, each of these blocks on the interface have lots of information. And of course, there's ways to harvest that information in a variety of ways. But let me just show you one other screen. This one's a different view, simplified neighborhood dashboard. You see a similar individual home dashboard right here in the middle, just about, with the percent solar at 129. You see there's also a view of the neighborhood there. It's all the way over to the far left. And a view of the power flows all the way to the right there. Those little dots that are moving along on the representative power lines. And you can toggle this. It's actually showing real flows of power here based in terms of amount and velocity. But you can also toggle it over to historical data for troubleshooting or reference, or checking back to see what may have happened if there was an incident. You can see it's all color coded. And in case you haven't noticed, that's a little bit hard to do with electrons because they're not so cooperative, but just kidding. So in this case, you can see the PV generation flows. The PV is coming off the rooftops there in those yellow or orangish dots. You can also see the nanogrid service flows. That's the blue dots going into the buildings. So that would be AC power going in after it's inverted at the nanogrid boxes out there. And you see the grid bus, which is that mesh, hybrid mesh bus-like topology, where the green dots are moving and ultimately going down to the community microgrid. And if there's excess power, as I think there is right now, or at least it's showing that there's excess power in the neighborhood, that it would be inverted and put back on the grid. Although it may look like a video game, this is the real thing. It shows everything in real time. Although in this case, you're seeing a recording of it. We did make the recording by just literally recording real-time dashboard. What I've shown you is the original pilot of the project, which was completed and put into operation last year. It services live occupied buildings and an operating space on the Air Force Base. And despite the fact that Emera's engineers have continued to do stress testing of the grid using the load bank over at the Sandia lab there in that, I think it was N9 nanogrid, the grid has performed flawlessly for almost a year now. Work is currently underway at this location on 3 more non-contiguous neighborhoods. Each will follow the same basic configuration and will be ultimately interconnected by a higher voltage DC bus and will have redundant connections to the utility for further assurance of resiliency. Meanwhile, several other residential development projects in Mexico and Florida, in New Mexico and Florida, are underway using this approach, lest you thought it was just for the military base or for testing purposes. They will all have a similar modular approach with a kind of a plug and play capability of nanogrids. And here's one example, a rendering of a community that will be powered this way in Mesa del Sol, home of several other interesting microgrids. Notice that the buildings don't all have the same solar exposure. And this is where the networking really comes into play. The same is true for the batteries. They're a shared resource, which makes each battery install more economical and right-sized, with the community microgrid backing up any issues at the nanogrid level. According to the developers, they think this will be a truly resilient, efficient, and environmentally responsible community. And oh, by the way, for you architects out there that I also mentioned, it looks cool, it looks good. Place a lot of us would love to live. But Emera isn't the only one to recognize the advantages of this grid of grid concept. Others are moving in the same direction. The 3 fundamental themes that unite these efforts are mesh networking, which is allowing the virtual configuration of sourcing, storage, and loads; DC coupling and busing, which is simplifying the interconnect by making it asynchronous and a better native match of power form to sources and loads and their eventual potential move to a digital form; and finally, distributed intelligent controls, where each unit can be autonomous and self-reliant when necessary, but operate in a self-enlightened cooperative way with the whole community when possible. And if you doubt the eventuality of a global grid of grids, check this one out. While it may sound crazy insane, Australia will soon start exporting sunshine power, solar generated electricity, to Asia via a 3,800 kilometer cable, affectionately called the Sun Cable. And this is from a country that is the world's third largest fossil fuel exporter. The Sun Cable project initially involves a 10 gigawatt capacity solar farm with about 22 gigawatt hours of battery storage. So global grid of grids, bring it on. Unfortunately, that's all the time we have for today, but I'd like to conclude by saying that the eMERGE Alliance continues to work towards completing new Vanguard power standards to achieve net zero energy buildings and campuses in a highly resilient neighborhood and community microgrid format. The rest of the portfolio standards work at eMERGE includes residential nanogrids, commercial industrial nanogrids, information and telecommunications, ICT technology nanogrids, AV charging infrastructure, indoor agriculture nanogrids, DC metering, that's revenue grade metering, and dual input AC/DC power supplies. The eMERGE Alliance is a nonprofit open industry association containing commercial, government, and academic member organizations who are developing standards leading to the rapid adoption of hybrid AC/DC microgrids in commercial and industrial and residential buildings, neighborhoods, and communities. eMERGE standards integrate the buildings and campus infrastructures, power and controls, and devices in the microgrid platforms to facilitate the hybrid use of both AC and DC power. The standards facilitate greater energy resiliency and sustainability while maximizing the potential use of distributed clean and renewable local energy. And you can learn more about us at www.emergealliance.org, or for direct support, send us a note at help@emergealliance.org. The eMERGE participates throughout the year in SPI, ESI conferences and events, including North American Smart Energy Week, this one, the largest event in North America, where we have been facilitating the demonstration of live microgrids that have provided power to previous face-to-face shows. In this year's virtual event, eMERGE is proud to co-host the Smart Energy Microgrid track in the program. Thank you again, and I hope to see you tomorrow at 3 p.m. for more exciting information about the grid of grids. Have a great day.
Well, first and foremost, the health and safety of our employees and their families, our customers, partners, and the communities in which we do business is of paramount importance to us. Early on in the crisis, our HSE team worked tirelessly to develop clear and consistent guidelines for our employees related to COVID-19. We've enforced preventative and protective practices across the board and have also adopted CDC recommendations relating to cleaning and sanitizing of our office locations and also our construction and operations sites. And at this time, other than employees involved in essential activities, meaning those associated with construction and operation of renewable energy facilities, our employee base is working virtually. On the business front, we're constructing close to 2 gigawatts of renewable energy facilities at this time for completion by the end of the year. And one area we're spending a tremendous amount of time monitoring is supply chain associated with key components. It's a very dynamic situation right now, and the situation is changing weekly, if not daily, as lockdown and similar type restrictions rotate around the globe. You know, at this time, we remain determined to complete all these projects in 2020, but it's not a given. It's a very complex situation, and it requires innovative thinking day in and day out to work around the new challenges as they arise. On a positive note, we do see continued customer interest in procuring renewable energy. Our customers, for the most part, are taking a long view and they're continuing on with their renewable energy procurement plans. And though we've seen some slight delays in procurement schedules, for the most part, contract negotiations are continuing and contracts are being signed. And this is all being done virtually, which is very interesting for all of us. In fact, we had a really good first quarter in this regard, having signed a few very large solar and solar plus storage contracts in the United States. So last thing I'd say is that our parent company, EDF, is a long-term company with a long-term perspective. We think we're equipped to navigate through the current market conditions, and we remain committed to our longer-term renewable energy goals. EDF Renewables plans to be there on the other side of the COVID-19 crisis.
Hi everyone. My name is Jorge Lizondo. I'm a CTO and co-founder of Hela Technologies. I'm very glad here to be at SPI, giving a presentation about distributed and semi-autonomous DER system control. Hela Technologies is a company that I started in 2015 as a result of being in the field and trying to build microgrid systems. And the whole idea of the company is that we want to build systems from the ground up, starting with the DERs and then interconnecting them to form microgrids, fleets, or whatever type of system we want. This means moving from a centralized control paradigm that you can see here on the left to a more decentralized or distributed one, where the assets interact with each other instead of having one authority telling them what to do. This whole concept of the decentralized approach to systems, to microgrids, started when I participated. I was invited to consult and to help in building a microgrid system in Sonoma, California. This microgrid is called the Stone Farm Microgrid, and it's a beautiful system. It started just as a solar plus storage system to provide power to some loads, which in this case is a vineyard, but it evolved into a living laboratory. So this project was started in 2013, and 7 years later, it's a fully operational system with solar panels that can be controlled and soft-curtailed. It has 9 different types of batteries that have been tested, and most of them are still operational. I'll talk about the different technologies later in the presentation. It also has a gas turbine that we can start or stop, and it uses natural gas from the utility. Interestingly, we also have a hydrogen system there that has an electrolyzer to produce the hydrogen. Then we can store that, and then we can use it in fuel cells. It has controllable loads like EVs, motors, pumps, HVACs, etc. And the capabilities of this system is very diverse. We can be grid tied and do some economic dispatch to save money for the customer. We can provide grid support. We can go to island mode during blackouts that is very common in that this part of the country because of fires. And when we're in island mode, we have very robust operation with dual master operation. We can also seamless transition between islanding and reconnection. And we deal, as I say, with multiple energy sources like heat, hydrogen, water, electricity. So this was a very interesting system. And from there, we actually went to other systems. Let's see if I can. Okay. To other systems, we have deployed fleets and microgrids across the country. In Colorado, where we have a residential development, Solar Farm, I mentioned. We have other deployments also in California as well. Beside this one, we have done projects in Massachusetts, Louisiana, New Mexico, Tennessee. Not all of them are listed here, but in this slide, I want to provide a glimpse of the variety of projects that we have been able to do. Now, these are all different projects, but they share the characteristic that they all have decentralized control, right? And the reason we did that is because when we were doing these projects, what we learned is that these DER systems, usually microgrids, are collections of disparate energy resources that were not designed to work together. The reasons that they were not and they don't play well together is what we list here as the challenges. These are the three main challenges that we discover, we synthesize for microgrids. So the first one is that the ecosystem is non-standardized, right? So you have all these different protocols, all these different characteristics on the elements that make them very heterogeneous. The second main challenge is that these systems are very complex, and you have to deal with time constants from sub-second for fast variations to day to night variations in solar production to seasonal issues, right? So if, for example, in the summer, you have a lot of solar, in the winter you don't have, so you have to make different decisions depending on the season. And the third main challenge is that most of these systems are designed with a rigid structure, meaning that they select the components, they tie them together, they put a centralized control usually, and then if you want to make any change, that takes a lot of work. So for example, if the customer suddenly wants to increase the load because he wants to move from a, let's say, gas-based cooking system to an electric-based one, and your electric load is going to go up, it's very hard to change the system. Or if you add, for example, electric vehicles, now you want to control the electric vehicles and also increase your solar production and maybe add more batteries or change your system. Usually, microgrids are not designed to have that flexibility, and that's a big challenge. What we did in Gela, we solved these main challenges by creating what we call the microgrid object or a building block. You can see here on the diagram that we have these units here that say IQ, and we put one of those in front of each DER in the system. So if you have gas turbine, you put a device right there. If you have solar, you put devices right there. If you have batteries, you can also put device right there. And then they connect together and they interact. You could have a central controller. We usually have like what is shown here, mostly for data collection in a single server, and also for dashboards. So if you want to see everything in one single place, you can have a controller. It's actually not making any control decisions, but you can have it to display the information. The advantage of this building block approach or object approach to building the systems is that first, well, you standardize the system, right? Because now when you are trying to interact with a particular resource in your system, you're actually going to this object that has functions and has the data. So you don't have to worry about if it's a battery or a solar or a gas turbine. It's all homogenized. The second one is that the complexities of each of these elements is now hidden behind the controller, right? The distributed controller. So a lot of the decision making or all the complexity of the type of variables and the capabilities that the external user doesn't have to worry about. The controller encapsulates all that diversity. And the third one is that it's very modular and scalable, because if you add something new, you can just put a new controller, right? So if now you want to add, for example, a gas turbine to this system, you add a new controller, that controller starts interacting with the rest, and you still have a system. You don't have to change anything in the rest of the system. You just add one more player. So they simplify the process of growing microgrids and systems over time. And it doesn't matter what the characteristics of the asset is, right? It can be a gas turbine, as I said, or it can be a load. We have dealt with loads many times, controlling EVs, HVACs, even VFDs, variable frequency drives. And the whole idea of the control system that we want to make the system look like a single entity, right? So if, for example, you want to connect to a utility and provide services, you don't want for the battery to have a different service than the gas turbine. You want everything to react together, right? That's part of the definition of microgrid. You have a management or optimization of the system so that it reacts as a single entity. All right. An interesting analogy to this approach to systems, the decentralized approach to system, is that of object-oriented programming. In software development, in the old days, software used to be done in a procedural way, meaning that you write your functions and then you write procedures and you tie them together, and then that's your code, right? It was a very procedural. It's called procedural, but it's very sequential, right? And then there was a complete revolution on the way the software is built, in that people created these objects, and the objects have data and functions themselves, and then the objects can interact with each other to achieve the entire software goal, right? Well, what we're trying to do in HALA is the same exact concept applied to DER systems and microgrids. So going from a centralized approach, which is equivalent to the procedural approach, where you have one controller collecting data from everyone, processing the data, and then sending dispatch signals, to a more DER-centric, where the DERs have functions and have data and they interact with each other. So you can see in the diagram here that moving from a procedural to an object-oriented approach is the same as moving from a centralized approach to microgrid control to a decentralized. The advantages of this object-oriented approach and the decentralized approach are the same. So you have separation of concerns. So each DER has only a concern for itself. It's extremely modular. You can remove one object and it doesn't really matter. You can remove one object to improve it. It doesn't matter. It doesn't affect the rest. So it's also very reusable. It's simpler to maintain because you have these objects. It's, you hide the complexity, as I was saying. You can port functions, and the collaboration is just simpler. So there's a lot of advantages in building a system like this. And as I will mention a little bit, you can also build any system, any form of system you want, because you have building blocks, right? So I'll get to that. This is how the building block creator looks like. I call it the building block creator because these controllers actually are what you put in front of each DER, and you can create, and then you convert them in building blocks. Actually, I have also one here. You can see a newer version. So it's a small device that you can install in front of each DER, and this does four things. The first one is that it simplifies the installation because it has all the ports that you need to connect to any DER. It has a lot of protocol compatibility, so you can connect to almost anything and translate protocol from one to another. The third one is that it collects data. So you have data per DER at the DER controller. You can also aggregate data, but each one of these devices aggregate the data. So it serves also as a database. And the fourth one is that they have what I call here selfish operation, meaning that they all make decisions for each other, and then you can still coordinate them to achieve a common goal. This is based on game theory, right? So in game theory, you have different players making their own decisions, but they still can achieve their own goal. And there's other advantages, for example, enhanced security, being able to deal with multiple energies, and I will go into that in a second. So going into the details of the advantages, I think the most important one is that we are compatible with any vendor. So in a sense, we're vendor agnostic. So this is a map of the Stony Farm microgrid, just to give you an example of the diversity of resources that we have used in the project. So going from a Geiner electrolyzer, fuel cells from plug power, simplified batteries, Tesla batteries, LG Cam batteries, with different inverters from SolarEdge, Schneider, Dynapower, SMA, Outback. So this system, as I say, the Stony Farm microgrid is a living laboratory. So although it started much simpler, we grew it to make it a laboratory to test all these different technologies. And it works very smoothly together. You can see here that, by having each DR making its own decision, you can still achieve common goals. So in the first figure here, what you're seeing is 3 of the DRs. I mean, there's many, but if you try to plot all of them, it gets very complicated. But each DR is making its own decision on what to do at a particular time, and you can still achieve a common goal, meaning that this is the power that we commanded the microgrid as a whole to import or export to the grid. So this is 0, and this is exported to the grid. So the dashed line is the set point. So here, for example, we command the microgrid to export to the grid. This is real data from the Stony Farm microgrid. So when we commanded it to export 50 kilowatts, it just did, right? Then all the resources work together to achieve that goal. And then we went down to import 10 kilowatts and then keep it at 0, and then start importing 25 kilowatts for a while, and then go back to 0. And all these interactions, there's a lot of interaction going on inside to be able to achieve these goals. But it's all very seamless because it's all based on decentralized decision making. You can also actually make them do more advanced things. For example, you can make the output of the microgrid depending on the frequency, in a sense, providing frequency support to the utility. What that means is that the frequency of the utility is going down. You can make your entire system start injecting power, kind of like helping the grid, because if the frequency is going down, generators are slowing down in power plants. So that means there's a lot of load. So you export power, then you can help them, right? So you can see if frequency goes down here, this is the frequency, you're going to start exporting. But this is just to show that you can control your system as a group instead of having to deal with individual elements. Now you can deal with a group. And this is a video of another project that we have, also just to show how seamless the operation is, a short video. And this is a project in Albuquerque, New Mexico, that we did with Emera Technologies. And in this system, you have, it's a DC microgrid, just to start, 750 volt DC. There's a lot of batteries. You can count 1 battery here, 2, 3, 4, 5, 6, 7, 8 batteries. You have another larger battery here. There's a centralized battery. And then you have some solar, you have generators that are not running in this particular video, but they can run. And then you have an interconnection to the grid through an inverter, because it's a DC microgrid. So the AC from the utility has to go through an inverter to convert to DC. And then all these batteries have loads because they are actually powering houses. And there's an inverter here to power the house. So this video shows how everything runs very smoothly, and all these batteries are making decisions for themselves. There's a HALA building block creator, a HALA controller in each one of these batteries, and they just interact to achieve a common goal and maintain the batteries operational. This was, you can see that this is usually a 25 kilowatt system, so it is either early in the morning or late in the afternoon. So there's not a lot of solar. Very important they read from the grid, but all these decisions are made in a decentralized way, and it just works very smoothly. Going to the next slide. Another great advantage of the approach that we use for microgrids is that it's technology agnostic, not only from the burn-door perspective, but also on the type of energy that you are dealing with. So we have dealt, for example, with battery systems, which are very common. You have an inverter right here that is interacting with the system, the microgrid in this side. And then you have your battery here to a DC converter, and you can control this as a group. But just as simple to control this, you can also control, for example, a load. We have controlled a lot of loads that are, an induction motor with a pump, and the interaction with the microgrid is through a BFD, and then you store energy actually as pressurized water. Now, this is not energy you can recover, but it's energy that you can store there for the water loads to be used there. So you can play with how you store your energy there. So it's another energy type of system. In the storage farm microgrid in particular, we have actually dealt also with hydrogen, which is an interesting technology where you can take electricity from microgrid, convert it to hydrogen, pressurize it in tanks, and store it there to then use it in hydrogen loads, which could be from an electric vehicle, a hydrogen vehicle. And we had in that project 3 hydrogen vehicles refueling from hydrogen produced on the site. So it was a very interesting experience. We were taking solar energy, put it in as hydrogen, and then just getting a vehicle right there, plugging it in a fueling station, and 5 minutes later, you have 200 miles to go around, all with hydrogen. We also had electric vehicles in that site, so we were able to test the difference, right? It's more efficient to do that through an electric vehicle, but it's more convenient to do it through a hydrogen vehicle because it's very fast. This hydrogen can also be used in fuel cells, so we play a lot with these things. We also, controlled heat as an energy type. So this is very technology agnostic. Also very important is that this approach of object-oriented approach to microgrid, as I call it, or building block approach, is that you can build systems however you like. It can be, because you have building blocks that you can put together to form either centralized systems, and we have in which all the resources are shared by the community. And the storage farm, even if it's not only one resource that is shared by the entire vineyard, it's still a centralized type system. What I'm calling a centralized type system, because all the resources are shared among all the loads. So there's not a particular resource, a particular battery for a particular load. So they are all shared together. Other type of system, for example, a system within Colorado, is a distributed system where each load has its own resource. Right? So in that case, we have houses where every house has its own battery. And then if there's a blackout, the battery can just disconnect from the grid and still be an island, but it's house by house. When the grid is there, then you can aggregate them as a group. Sometimes we call this type of systems, when the houses are not co-located, we call them fleets, and some other people call them fleets as well. But it's a type of system that is distributed. It's inherently different from the centralized or community shared resources. We have also done hybrid, where there's some resources that are shared by the community and some resources that are house by house, like the video I showed above, where each house has its own battery system. But also there's shared resources, shared solar and shared batteries. We did a project like that in New Mexico, and we're building one like that in Florida. We have other projects across the country, but they're all of these type of systems. And here, by the way, I'm using houses as a reference for the load, but not all of our projects are residential, right? It can be CNI, or it can be other type of loads. So those are the advantages. And just to finalize the presentation, this capability of being very capable of playing with any vendor, any technology, and any type of architecture led us to work with many players in the industry. So we work with project developers to do integration and to install the systems. So we do project through them. We work also with utilities. So we have some of our customers that are utilities directly, and we interact with them, provide them services. And we also work a lot with vendors, so battery vendors and inverter manufacturers that want to make their system building blocks so they can be very easily aggregated. So we're always looking for people to work with. We are open for business. So, happy to answer any questions. Thank you very much.
The world brings new energy solutions. City services, local businesses, and neighborhoods need cleaner, affordable, reliable energy delivered safely. Electricity needs to be smart and future-proof. But new solutions are complicated. They're tough to implement and don't integrate easily into existing utility systems. None solve all the problems. Until now. Introducing Block Energy, the smart energy platform designed to eliminate complexity and risk. Block Energy is a world's first, a fully functioning power system with plug-and-play technology that's purpose-built to work with utilities, delivering safe, cleaner energy with advanced resilience. Block Energy's simple kit of parts is modular and scalable to adapt to changing requirements and growing communities. No customized engineering or design required. Here's how it works. The system connects local generation and storage throughout communities of all sizes in self-sustaining block loops, using smart distributed controls, able to operate independently and interoperate seamlessly with the local utility grid. As communities grow, Block Energy expands without disruption, delivering truly frictionless installation and operation. The result is the most advanced distributed local power available today for neighborhoods and communities. Block Energy is part of the Emera family, active in Canada, the US, and the Caribbean, with 2.5 million customers, $34 billion in assets, and over $6 billion in annual revenue. And now, makers of Block Energy. Military tested, Block Energy is delivering the new standard for security and resiliency on Kirtland Air Force Base right now. Thank you to our development partners, Kirtland Air Force Base, Sandia National Labs, and the Department of Energy's Distributed Energy Technology Lab for making Block Energy's pilot program a success. Local networked grids are the future standard of electricity. With builds in progress across the U.S., Block Energy is the future of energy delivered today.
Hello, my name is Becca Jones-Albertus, and I'm the Director of the Solar Energy Technologies Office at the U.S. Department of Energy. Today, the department made an exciting announcement. Daniel Simmons, the Assistant Secretary for Energy Efficiency and Renewable Energy, announced the 2 grand prize winners of the American-made Solar Prize Round 2. The Solar Prize is a competition designed to invigorate American innovation in energy and manufacturing and rapidly bring solar technologies to market. The 2 winning teams announced today made tremendous progress over the year in which they were competing for the prize. Each of our winners is receiving $500,000 in cash prizes and $75,000 in vouchers redeemable at the national laboratories and other partner facilities. The first winner is Resilient Power Systems from Georgetown, Texas. This team is developing a solution that enables interconnection between solar, energy storage, and other energy resources, utilizing a novel bandgap technology platform. Their power router enables direct connection of these resources to the medium voltage distribution grid, integrating transformers and inverters into a single unit. The wide bandgap technology design is ideal for scaling their prototypes for domestic manufacturing. The second winner is Sunflex Solar from Tempe, Arizona. This team is replacing high-cost copper backsheets for high-efficiency silicon solar cells with lower-cost aluminum. They're using a high-speed laser to weld the aluminum backsheet to the silicon wafer and have secured a path to manufacturing this technology domestically to produce high-efficiency, cost-competitive domestic solar modules. Congratulations to these 2 teams. As a reminder, round 4 of the Solar Prize has just opened for competitors. So if you have a great idea for a new solar technology, submit your entry by October 8th. Also, round 3 of the prize is currently underway, and those grand prize winners will be determined and announced in December 2020. So stay tuned for that. Congratulations again to Resilient Power Systems and Sunflex Solar.
Hi, I'm David Peabody, and I'm going to be talking today about a microgrid project that we are working on right now in Fairmount Heights, Maryland. I'm going to introduce sort of the background of that, and then Dusan Berlik, who is the designer of the system, will jump in and explain it. Could we go to the next slide? So we've been working in high performance buildings and passive houses for the last 10 years or so. And only really in the last 3 years have we gotten involved in zero energy buildings. One of the reasons that we became interested in doing buildings with locally generated energy was just the inefficiency of the grid. Here we were doing super efficient buildings, but they were in a super inefficient grid. So locally distributed seemed to make the most sense to me. And I learned a lot about this from people like David Geary and Terry Hill. It's part of the Emerge Alliance. We did a project, let's go to the next slide. We did a project, which is on the right, about 5 years ago, which was a zero energy passive house that it's an affordable infill house for a nonprofit. And that project was quite a success. It uses about 7,000 kilowatt hours per year. So it needs about a 6 solar panel array. That is not a solar house, but we calculated. Well, the developer came back to us about 3 years ago and said, we'd like to do a whole street of these houses. And we'd like to make them net zero ready. So it occurred to me that here we had 6 contiguous houses. What better opportunity than that to do a microgrid? And the developer was fine with that, but said, we can't afford it. It's hard enough for us to do this as affordable housing developers as we're doing it. If you can get the money, go to it. So nothing really happened for 2 years. Nobody would even talk to us about it. But then Maryland Energy Administration came out with a grant for a microgrid planning study. And we jumped at it. And I teamed up with Doosan, with Direct Energy Partners and Interface Engineering, who we were working with on another project. And we went after that grant and we got it. That then led to our being able to have some credibility, I guess. And Emera Technologies got very interested in the project as a pilot project. So now we're developing with Emera, which will fund the microgrid. We're developing a pilot project with Pepco, and that's now in regulatory approval. So it looks like the project really is going to have legs. And so we're basically using this same prototype for 6 houses that will be linked together in a community microgrid. And at this point, I think I'm going to get out of the way and let, oh, I'm sorry. I have some more slides. So the background of this was that we have, I guess in the process of doing this, I realized that high performance buildings were the only answer when you're putting together microgrids as we move into a transactive energy economy. That the future is that we're going to be seeing buildings as virtual power plants, and the more efficient they are, the more affordable and economic they are to own and operate. So if you look on the left, you see the amount of roof area that a standard construction house uses. On the right, you see the amount of roof area that a passive house uses for solar. And then if you go to the next slide, you can see that the standard construction has about 46% of its roof left for energy generation, whereas the passive house on the right has about 83%, I think, left for energy generation. So I guess that would be fine if you were doing a standard construction and wanted to live in a one-story house or be in a one-story office building, like a data center. But if you wanted to, as most buildings do, to go have a basement, have livable space on more than one story, that's a different situation. And so let's look at the next slide. You can see on the left that basically standard construction will give you about 1.5 to 2 stories of floor area that's supported by its roof, whereas on the right you see that passive construction, high performance construction, gives you about 6 stories. So I think that's going to be a real motivating factor as architects design buildings in this new economy, which we see coming. And it's not going to be any more concerns about climate or anything else. It's just going to be sheer economics that's going to drive this. So I'll turn it over now to Doosan to talk about this project.
Great. Thank you for that overview and introduction, David. Let me just start by briefly introducing myself, Direct Energy Partners and Decor Technologies. My name is Dusan Berlik, and I'm the founder and CEO of Direct Energy Partners, Inc. The DEP focuses on designing scalable DC microgrids, which increase our customers' operational autonomy while reducing their overall energy usage and operating costs. Our system designs are at least 10% more efficient than the industry standard and have a 30% lower total cost of ownership. We focus on local energy generation, a direct current backbone infrastructure, and DC loads, which produce systems that are more resilient, reliable, and energy efficient than any others on the planet. Decor Technologies is a new initiative started by 2 DC microgrid engineering firms, DC Energy and DEP. We started our collaboration earlier this year in an effort to accelerate the design process and deployment of DC microgrids worldwide. With our joint expertise and resources, we strive to lower the barriers of entry to DC systems of all sizes. To date, our collaboration has yielded the development of a new software tool, which allows us to design the microgrid systems with greater efficiency and was utilized in the Fairmount Heights project. Before I get into some of the details of this Fairmount Heights project, I'd like to take a moment and reflect upon the importance of designing resilient communities. Our existing electrical infrastructure currently sits at an inflection point poised to take advantage of incredible advances in technology or to become overwhelmed by rapidly increasing demand, aging legacy equipment, and vulnerable supply chains. Without a shift in how the world approaches energy generation and distribution, energy costs will continue to rise, outages will become increasingly more frequent, and our energy security will be threatened. In order to successfully fulfill their mission, facilities and communities around the world must be able to operate from a variety of energy sources and not be dependent upon a single point of failure. Our study involved the technical design, planning, permitting, and financial modeling of a community microgrid for 6 affordable single-family residences. The homes in this project have the capability to share their locally generated and stored solar energy with each other via a direct current power distribution bus. They have the ability to operate during extended grid outages, and because of the availability of a DC power distribution network, each home is equipped with high-efficiency DC lighting and DC appliances, which can operate alongside legacy AC appliances even during islanded modes of operation. On average, DC power is at least 9% more efficient in the utilization of energy from the source of generation to the source of consumption. The efficiency gain can directly be attributed to eliminating AC-DC conversion devices from various sources of generation and loads. This improvement in efficiency directly translates into cost savings and overall improvement in operating reliability. The technology exists today to interconnect buildings with a dedicated DC power distribution network. What is missing, however, is the approach to deploying these microgrids and a business model which allows these systems to be deployed, owned, and operated at scale. I'd like to provide a quick overview of how microgrids connect to our electric utility. This will be important to understand later on in the presentation. While there are several variations of microgrids out there of different sizes, types, and topologies, the way they connect to our existing electrical infrastructure can be boiled down to 2 options: a front-of-the-meter connection or a behind-the-meter connection. The term behind the meter is used when describing solar and energy storage systems that power your home or building without needing the utility. In essence, a behind the meter refers to power equipment that is located on site in your home or building. The difference between a behind the meter and front of the meter system really comes down to the microgrid's position in relation to the electric utilities meter. A behind the meter system provides power that can be used on site without passing through a meter, whereas an in front of the meter system provides power to offsite locations and requires that all power must pass through an electric meter before reaching an end user. So now that we understand the distinction between behind the meter and in front of the meter solution, let's take a look at a typical home and how it is wired into our existing electrical grid. This is an in front of the meter configuration. As you can see in this overly simplified drawing, which connects the utility's electrical distribution lines through an area transformer. This transformer is responsible for changing the voltage from the utility's medium voltage, 13.8 kilovolts, AC to 240 volts AC, which can be found in our homes today. From an overly simplistic point of view, electric companies can be thought of as stewards of our power lines. They deliver power generated to our homes via long-distance transmission lines and distribute that power to our homes via local power distribution lines. Electric companies maintain the quality of their physical power distribution network to ensure that power can reliably move between points of generation and points of consumption. They're also responsible for securing enough generation capacity to meet the demands of the homes attached to their power distribution network. Some of the electricity gets generated locally, and some of it gets purchased and delivered to us from elsewhere. And so this is important to understand as we move forward with this presentation. This configuration has served us well for the longest time. However, it has its disadvantages. If the area transformer, shown in the yellow box on this slide, goes down, or any of the utility lines become damaged in the power distribution network, the homes are going to be stranded without any power, as this architecture is prone to single points of failure. Here's an example of a typical solar plus storage installation. This configuration connects new electrical generation and storage capacity behind the meter. Some of the more notable benefits of this configuration include the home's ability to supplement its demand by generating power from solar panels and operate without the utility in case of a grid outage. This is not a bad way to increase your home's resilience or reduce your home's electrical bill during high utility peak hours. Your power outage rifle capability, however, solely depends on how much energy storage you have on site to meet the demands of your home. One notable disadvantage of this configuration is that in states with regulated utility power, you're actually prohibited from being able to transfer power between property lines. To be clear, a behind-the-meter microgrid configuration located in a state with regulated utilities is not allowed to export power across property lines. The only way to export any excess power generated across property lines in a state with regulated utilities is through the utility's ownership of the microgrid itself. And that's exactly what we did with the Fairmount Heights microgrid. The Fairmount Heights microgrid sits between the residential homes and the electric company's power grid. It is a home-sized electrical system which allows the homes to operate without the larger power grid. It uses local power generation, such as solar panels, coupled with battery storage and power from neighboring homes. Effectively, we have given the homes the ability to decide where they get their power from in order to keep the lights on. The homes can decide to purchase electricity directly from the electric power grid, consume the locally generated or stored power, or take electricity from the larger microgrid itself. In a moment of crisis, our microgrid can connect to and disconnect from the electric company's power grid to keep the power on to the homeowners. The microgrid provides electrical resilience. So this particular microgrid provides electrical resilience in 3 different ways. One is that it powers the homes during severe weather, utility-generated blackouts, or mandated shutdowns. The second is that it leverages locally generated power from neighboring homes to power the homes in need. And the third is that it simplifies the electric supply chain by making the homes less reliant on fuels, which are inherently vulnerable to disruptions or attacks. Now let's take a closer look at how the homes generate, distribute, and consume electricity within the community and interact with the utility. Each home generates its own power by converting sun rays to electricity via rooftop solar panels. Each home consumes the locally generated electricity to keep the homes warm, well-lit, and connected. Each home additionally stores the electricity in batteries, so the power can be used when the sun doesn't shine or the electric company's power grid is not available. Additionally, each home has the ability to share power with its neighboring homes during crisis. It has the ability to share any excess generation with a community-centric battery or supply reserve power for utility interactive services. Finally, each home connects to a community-scale battery, which is large enough to provide extra power to each home within the community if called upon, and or act as a single point of connection to the electric company's power grid. This configuration not only benefits the homeowners, but it also benefits the electric power company. For example, the homes can stop drawing power from the electric power grid during heat waves, and in exchange, the electric company can reward homeowners with substantial cash payments. So with this particular configuration, we have not only increased the resiliency of the homes, we have also made sure that this new electrical system can play nicely with the utility and actually benefit the utility itself. In this particular drawing, the white boxes adjacent to each home contain batteries and power conversion equipment to facilitate energy transactions between the homes and the central power plant, which is shown as a larger standalone white box in the middle. The central power plant contains energy storage and power conversion equipment to facilitate energy transactions between the utility, power grid, and individual homes. DC energy generated from solar panels is stored in DC batteries and either gets consumed by the homes as AC or distributed to the community pool as DC. Any surplus locally generated electricity gets distributed to the community power plant, which again is depicted in this slide as a centrally located white box. In a moment of crisis, each home is responsible for powering itself first, and only then it's responsible for the community itself. Subsequently, if needed, each home can help itself with sharing power and helping out the utility as well. As previously noted, in order to improve the overall operating efficiency of the homes, we focused on eliminating the number of AC-DC conversion points between sources of generation and sources of consumption. Unlike your typical home, which has a single electrical power distribution panel, the Fairmount Heights residences are planned to have a new direct current power distribution panel, which sits alongside its legacy AC counterpart. This new DC panel allows the homes to draw DC power directly from the resilient DC bus, connecting the homes and distribute that power to DC loads located within the homes in the most efficient manner possible. So far, we're planning to add the following DC loads to homes: ERVs, mini splits, lights, receptacles, and in the future, appliances as they become more readily available. The efficiency improvement over legacy AC systems for generating, distributing, and consuming power as DC is about 9%. In other words, a DC home requires 9% less solar energy, 9% less energy storage to accomplish the exact same thing as compared to the legacy AC homes. These are some significant savings as we're trying to design high efficiency and resilient homes. Some of the additional work that went into the generation of the feasibility study report for the Fairmount Heights project is the modeling of various microgrid topologies. We wanted to learn more about the benefits of connecting the homes together with a shared DC link and understand what it takes to scale the microgrids beyond just the 6 residences located in this demonstration project. The model we have developed to assess the benefits of various system architectures compares the CapEx and OpEx of each system configuration. The model subdivides the results according to the asset owner, which in this case is the utility and the individual homeowners. Unfortunately, you'll have to wait for the report to come out in order to learn more about our findings, so keep an eye out on it. The next thing I'd like to highlight is the Microgrid System Designer tool we've developed in order to facilitate a speedier design process of various microgrid configurations. What used to take several hours sketching up various microgrid configurations and assessing their behavior within the system now only takes several minutes. As you can see in this quick demonstration, the Microgrid System Designer lets you configure your microgrid in terms of building blocks. Each building block is unique in nature, and configurations set during the design process get preserved within the building blocks. This allows the system designer to check for microgrid component interoperability as soon as you place it on the schematic. This is a huge time saver, and it really allows you to compare and contrast various microgrid configurations very quickly and eliminate any kind of errors from your microgrid design. We found this tool to be a huge time saver for us, and therefore we'd like to open up the tool to early stage beta testers. So if you're interested in test driving the Microgrid System Designer and provide early feedback on its value to you and your organization, please feel free to contact me or visit us at dcoretechnologies.com to find out more about the schematic design tool. You can also find my contact at the end of this presentation. To summarize it all, it has always been our goal to demonstrate that building affordable, resilient, zero-energy communities are not just an idea, but can be a reality. While we've encountered a few barriers along the way, there really are no significant showstoppers that would prevent us from realizing this project. Nothing from a technical point of view, at least. We hope that the existence of the 60th Place microgrid community will be a dramatic accelerator of the distributed energy disruption which is already underway. And we look forward to taking this project beyond just a feasibility study and realizing it together with Emerald Technologies. I'd now like to thank you for the presentation.